Okay, class, welcome. We're going to be going over right now the exam extended response question. This one is about keychains, and a little hint and piece of advice. If you want to excel on your midterms, you should always check out your professor's thesis when they were in grad school. You might get a hint. Um, This is a simple keychain right here. It's the one that you were asked about. Okay. So this is not focused too well. Focus. Okay, that'll do. So they're asking the first question. This kind of guides you through the thinking. This carbon right here is what we're interested in, and we're going to label the hybridization of all the atoms, and then we'll come back to this guy. So first, we'll go left to right here. The oxygen, okay, it's got a double bond to carbon. So 1, 2, 3 groups ranged around it. It's trigonal planar. That would be sp2. Okay, because it needs an orbital for each of the lone pairs, and then an orbital for the sigma bond with the carbon. Then it leaves one p orbital for the pi bond with the carbon. This carbon, this is the interesting one for us. It's linear. It's just got one substituent on each side. So in order to achieve that sort of geometry, you have to have sp hybridization. And the other two p orbitals, as we'll draw out momentarily, are used to make pi bonds with the oxygen and the other carbon. So this guy is 2 sp. Lastly, this carbon kind of looks like the oxygen over here. It is also sp2 hybridized. It's got 3 groups around it, and the remaining p orbital is used to make a double bond with the central carbon. Okay, so the next part of this question asks you to draw the pi bonds in this ketene. And instead of just memorizing, SP for linear, SP2 is trigonal planar, let's think about where these geometries are coming from, and let's start with our valence orbitals. Okay, so carbon valence orbitals consist of a spherical 2s orbital. I'm just going to draw it here. It's in 3 dimensions, right? I'll label this X, Y, and Z. This is a 2s orbital, and I'm not going to worry about drawing any of the spherical nodes or anything like that. Just think of it as a ball. And then our p orbitals, right? We've got 2 p orbitals. We've got 3 of them. And you guys probably remember from Gen Chem, they look like dumbbells. So I'll label all the axes. This will be my 2px. And this oriented along the x-axis, and we'll shade it. It's kind of arbitrary how you shade it, but it's important that one is shaded and the other isn't. Represent the phases. And I'm running out of space, but we'll have just enough. Okay, so I'll draw the 2py and 2pz. X, Y, Z, X, Y, Z. And I'll just put it so the shaded part is in the positive direction as I've arbitrarily assigned. Okay, boom. So we got our 2s, 2px, 2py, 2pz. These are the atomic orbitals. Better yet, I'll call them the valence atomic orbitals of carbon. Okay. And we can combine them in various ways, right? Hybridize them to make new hybrid orbitals. And that being said, let's turn our attention to this central carbon in this ketene and talk about the arrangement of the carbons. So scroll down here. Okay, there's our middle carbon. We know that it has to make a single bond to the oxygen and to the other carbon, and those are with the sp hybrid orbitals. So we combine a 2s and a 2p orbital. Arbitrarily, we could call it the 2px orbital. I'll draw it out for the sake of clarity. So there'd be one of them overlapping with this would be a sp2 carbon, so csp2 orbital. Okay, that's going to make a bond, and the same is going to go over here with an oxygen sp2 orbital. Okay, so that's sort of your sigma bond framework. So this is labeling these orbitals individually. CSP, CSP, this is OSP2, this is a CSP2 hybrid orbital. And I haven't drawn any of the others in. All I've drawn is the carbon-carbon sigma bond, and then the carbon-oxygen sigma bond. But of course, the interesting part about this molecule is that the carbon has double bonds going to two separate atoms. Let me get this paper here. Okay. So let's talk about that. I'll redraw our ketene. And if you recall, we still have two p orbitals available with this carbon. We didn't do anything with them. I call them 2py and the 2pz orbitals. And they're still here, my ketene. Okay, we'll call this a 2pz. And the one coming out, going back into the page, is the 2py. Okay, and that is okay. Let's see. There we go. Oh, the glare is not favorable. Sucks. Okay, there we go. You can see that these p orbitals can overlap side by side with other p orbitals in nearby atoms to make pi bonds. And that's exactly what happens. So it's sort of arbitrary which way I put it, because we didn't draw any stereochemistry on this molecule. So we'll get into that later. I don't want to fuss over the details. Let's just say that these methyl groups are in the plane of the page. Then in order to make a pi bond with this carbon, remember this is an sp2 carbon, it also has a p orbital available still. Can overlap carbon to make a pi bond. So that's in phase, and that's in phase, and that's how you make a pi bond. Is you overlap two orbitals in phase side by side like this. Okay. So by drawing some scribbles in here to show the bonding interaction, I've sort of made the phasing unclear, so I'm gonna erase them. But I hope that's clear, the sort of interaction that we have there to make a bond. Okay, and this carbon still has one more p orbital that it can use to make a pi bond, and it does that with the oxygen. And for a bonding interaction to occur, it has to be in phase. So just like I did before, I'm gonna draw this. See the way they're interacting? The 2pz orbital going with the oxygen, and the 2py orbital going with the other carbon. Okay. So again, I'm gonna erase these scribbles so the phasing is clear. So for full credit, show the correct shading, geometry, and orientation of the p orbitals. If you drew something like this, you can expect full credit. You did a good job. Okay. Next, you're asked to draw a molecular orbital picture for the pi star orbital for the CO bond. Something I didn't go into here, and that we're not going to be too harsh about for the time being. When we're drawing these molecular orbitals, so those, we're not really drawing the MOs. We just wanted you guys to draw the p orbitals and how they align. But with the MOs, we've got to worry about something called coefficients. Sometimes the lobes are going to be bigger on one atom than the other in a molecular orbital. So just like you guys all probably saw in Gen Chem, when you combine two atomic orbitals, you get out two molecular orbitals. One is lower in energy, one is higher in energy. You've probably seen diagrams like this before. And I'm always going to be plugging P-Chem, urging you guys to take that and staying fresh on your math so that you can derive this sort of diagram. If you ever, you're a linear combination of atomic orbitals, combination of atomic orbitals. That's how we make molecular orbitals, right? And that describes bonding in organic molecules and sort of the theoretical framework all this is based off of. So I've got a p orbital over here and a p orbital over here. Oxygen p orbital and a carbon p orbital. I should be more specific here. O2p and C2p. Okay. Phases arbitrarily. And as we've drawn them, they each have one electron. We're not really worried about that. We're just worried about what the resulting orbitals will look like. I won't even draw the electron here. We know that it fills up the bonding orbital, but I'm not going to worry about it. So the bonding orbital, that's in phase overlap. They overlap properly, and you get out something that looks like this. Okay. This is carbon. This is oxygen. And oxygen is more electronegative, so it withdraws more electrons to it, and that's why its coefficient is larger. But the reverse is true in the anti-bonding orbital. So we call this pi. We call this pi star. Is the anti-bonding orbital. So there's the axis connected. Let's see, the phases are now off. And this is again carbon, and this is the oxygen atom. Drawing points. Okay. And they're splayed outwards. And this is an important angle here that we'll get into more when we're talking about carbonyl chemistry. And it's been shown experimentally in some really elegant experiments that this exactly what this angle is. I won't spoil it for you guys, but it's interesting. Okay, so there's the carbon oxygen pi bonding orbital and pi star anti-bonding orbital. So if you drew the pi star like this with proper shading, coefficients, and orientation, good job, full credit. Okay, move it down. Okay. All right, so mechanism. You guys are going to be drawing a lot of these curly arrows. So this is a nice representative problem. Get you started. Okay. 3. Oh, okay. The lone pairs are drawn to start with. Not drawn in product. Okay. Okay. So if you just look at the bonds being broken and formed, I think that typically gives you a good hint at how to draw a mechanism. So let's take a bit of an inventory. I'm going to go ahead and draw on the lone pairs as well while I'm at it. Okay, this oxygen has a negative charge, so it's got 3 lone pairs, and the nitrogen has a positive formal charge, no lone pairs. Okay, so let's take a bit of an inventory. It appears that there is no longer a pi bond between this carbon and this oxygen in the product. That bond has been removed and the oxygen has received some extra electrons. So I would draw a curly arrow like that, showing those 2 electrons in the pi bond going to the oxygen. And perhaps the most obvious change, we have formed a carbon-nitrogen bond, and nitrogen no longer has a lone pair. So something like this makes sense. Likewise, you can think of a lone pair on this nitrogen as being a partial negative charge, right? That nitrogen is electronegative and withdraws electron density from the methyl groups as well. So it's electron rich. And then this carbon, we all know how to draw resonance structures for carbonyl compounds like acetone. And if you draw that out, you'll see this has a delta plus. So a common theme, you'll see it over and over again, is electrons going from electron-rich sites to sites that are lacking in electron density. And we'll get into more terminology on this later, and you guys will get really good at pushing these arrows around. go into more detail, but I think that is sufficient for now. It's probably been too long of a video already anyway. So there it is, your extended response question answered. Hopefully I didn't make any mistakes. Okay. Good luck with the chemistry, everyone. Hope it went well.